of methane and its impacts on today's climate. First of all, there's Martin Krüger. Martin is from the Federal Institute for Geosciences and Natural Resources in Geomicrobiology of Germany. We have Helge Niemann from the Institute of Environmental Geosciences from the University of Basel, Switzerland. Matthias Haeckel from the Leibniz Institute of Marine Sciences, Germany. And next to me, Alina Stadnitskaia from the Royal Netherlands Institute for Sea Research. Please go ahead.
Good afternoon, everybody. Thank you for coming. And it is our pleasure to come over here again this year. Thank you very much for inviting us. So compared to the last year press conference, we will outline here more larger topics. So in our common presentation, we will talk about three actually subjects involved in the geomicrobiology in extreme environments. So that's why we have 4 talks today. And I will start with a bit generalizing and introducing the main statements of our 3 methane sessions, which are going to be on Friday. So apparently from the last year, we're still struggling to estimate global methane budgets. And what we understand that we have quite a big imbalance between methane sources, which are not identified yet completely, emissions and sinks. Therefore, the first part of this presentation will be given about the fate of methane and ecosystem response in marine and terrestrial environments. Helge Niemann, he is an expert in terrestrial methane cycle and trace gases, and myself, I will talk a bit about marine methane cycle, extreme environments, and also how it's impacting the climate. Then we will move to marine gas hydrates, new energy source, and climate disaster. Matthias will tell us what gas hydrates are, where they are, and what kind of research and development going in this research and, let's say, industrial applications. And we will finalize the conventional fossil fuels, which are limited nowadays. And Martin will talk about unconventional methane gas, which we can receive from shale, coal, or petroleum reservoirs. So going further, small molecules, as we see from our title of our press conference, but with the apparently big impact. Indeed, so methane can be a friend, and we all now know that it is an alternative to a gasoline fuel, so combustion, and potential future fuel. But simultaneously, it has a huge impact in our atmosphere since it is a stronger greenhouse gas. And it has a global warming potential 72 over the last 20 years, and which means that emission of 1 volume of CO2, of methane, sorry, will be equivalent to 72 volumes of methane. So actually it makes methane more dangerous greenhouse gas in atmosphere than CO2 currently. What we know, very briefly, current knowledge, it is known that all global methane cycle in the Earth is driven by microorganisms. In fact, it's a highly specialized anaerobic methanogenic archaea and aerobic methane oxidizing bacteria. Anaerobic means that these microorganisms living in environments which are, they don't contain any oxygen, and aerobic which contain oxygen. So methanogenesis, it's quite common processes on our Earth, and it is anaerobic process, so it's not tolerate any oxygen in the system. And methanotrophic can be both, as I said. So methanotrophic can be aerobic and can be carried out in anaerobic environments. And this is quite a special process. And oxidant, as you can say that, in marine environments is sulfate. And this process is called anaerobic oxidation of methane with sulfate. That's why we call it SOM. And it's performed by recently discovered in 2000, only 10 years ago, microorganism. It's a consortium of methanogenic archaea, or because it eats methane, so it's methanotrophic, which living in mutualistic consortia with the sulfate-reducing bacteria. In fact, there is two outcomes from this reaction, which is actually it's a net reaction, but intermediate are still unknown because these organisms are not cultured yet. So the outcome, it's a biomass, so what you see here, and it is a carbonate, calcium carbonate. So this, you see the example of these methane-related carbonates. So these stones are formed or induced by the activity of these microbes. So this is how these microbes, one of the example of these mats which are contained methanotrophic anaerobic consortia. And this reaction, apparently the main sink of methane in marine environments, since there is a lot of availability of sulfate, and actually almost 90% or even more of methane is removed from the global ocean due to these microbes. So they kind of formed a microbial filter, or marine microbial filter, how it's called now. So, but if we see on this slide, on this picture, so which is spectrometer, that is the methane concentration which we measured in satellite. And we see that the oceans, actually, they are not really contributing to the global methane budget. So the estimations from 1994, it was that the methane adds from 3 to 5% of methane to the global methane flux. However, if we look on the continents, so we see that especially the northern part, like Arctic, and especially the Eurasia part, contributes the most into the methane emissions. So what we have here, this is how Arctic, no, it's very simple sketch, how Arctic is looking now, and that deep-seated methane, so permafrosts, we know they are melted, and the deep-seated methane is dissipating and actually emitted in the water column, and as well in the permafrost area in the continents. So it can go from the so-called thermokarst lakes, I'll show you pictures later, and or it's often emitted near this, it's called ice wedges. It's also part of the ice complex which is full in Arctic areas. And what was measured during the different multiple weather stations around Arctic region worldwide, that since the 1970s, summer and winter temperatures increase, and that the time of the sea ice decreases. So we observe in a different scale changes in our climate in the north of our planet. So that is kind of what guys, when they see this picture, they say, what is it? It's not really directly clear what is the sketch here. So that is a NASA image, and this is Alina River. It's one of the biggest river in the Russian Arctic, and these are thermokarst lakes. So all of this is full of methane. Methane is coming. So these lakes, they're quite shallow, and they're now known to emit quite a lot of methane and CO2. So this is from this part of Arctic, Lina, as I said to you, and this is shelf of Alaska. So going further, so when we talk about global methane budget, what is important, global versus regional? So if we see on these three curves of temperature reconstructions from North Europe, it's black, it's for the last 600 years. And then we have a red one, which is belonging to northern Siberia, northern part of Siberia and eastern Siberia. We see that actually the temperature deviations were different in these regions. Therefore, when we approximate, when we make these measurements in a kind of different parts of our Earth, and when we see that, for instance, Arctic melts, but as known during 2008, the atmospheric methane in Arctic didn't change in general. So it is important actually to maintain a balance between detailed regional scale studies and a large scale perspectives. And it will help us to improve in temporal spatial reconstruction for climate models in global. Because when we kind of take some output of methane in one area, like it was, I'll show it later, was a recent science paper by Shakova, when the emissions of methane, which were measured during the summers from 2003 to 2008, actually calculating on this spot, was equal to the global methane budget for the whole. So that raises this question even higher. So that is exactly the pictures. It's coming from the Natalia Shachova's paper showing this huge methane release in the water column. And what is actually unknown, or what gap of knowledge we have, is the efficiency in the methane emission reduction scenarios, and we have to still assess it. And actually, emissions, we still don't know the whole sources to estimate it correctly. We don't know what kind of climate feedback on the global scale. As I mentioned, for instance, this small part of the Siberian shelf, it's here, it's Eastern Siberian Sea. And when we talk about the whole Arctic, so they are seeps intensively, but it doesn't mean that the whole Arctic seeps intensively. And of course, this imbalance between methane sources, emissions, sinks, increased significantly during the last years exactly in this area. That's why it's now become to be a topic, or let's say frontier scientific interest from the multidisciplinary geosciences. And now this is a kind of new part. It's ice. It's ice which was collected from the also different ice structures, ice complexes, massive ice and ice wedges. And if you see here, so this ice possesses a lot of bubbles, and these bubbles are syngenetic to this ice formation. This, for instance, piece of ice contributes possess organic matter, which also syngenetic to the ice formation. So in fact, this is another archive for the past or ice formation and to the climate, which was, for instance, in this case, this is Holocene ice. It was 10,000 years dated. So what kind of environments were during this time? And this subject is still not touched. So this is an ice which possesses a gas and methane as well. And now we're moving further to another ice-like structure. Yeah.
So I will continue and introduce methane hydrates as a potential energy source that many countries look into. So this here shows you the structure. This is how a massive gas hydrate, this is coming from Hydrate Ridge of Oregon, looks like, and of course it's burning. And when it starts to burn, it actually dissociates. So from 1 liter of hydrate, we will gain about 0.8 liter of water, and something like between 160 and 180 liters of methane gas is released. So this is the potential as an energy source, what's behind that. The second question then is, of course, where do gas hydrates form and why are they stable in the marine environment? And this is a diagram that shows you here the pressure and here the temperature. And in the blue shaded area, so at higher pressures and low temperatures, so where water is cold, hydrates actually form in the marine environment. And if we're getting too warm or too shallow, not enough water depth, then hydrates are not existent. And this becomes obvious here, for example. This is a graph from the bathymetry of the water depth at the Crimean Shelf, where we see in shallow water depths quite a few methane seeps. So methane gas bubbles actually are coming out of the sediment and are released into the water columns. These are several thousands of these seeps. And if we go deeper into the Black Sea, then here at something like 730 meter water depth, hydrates actually become stable, and these methane gas seeps almost disappear. There are still a few, but they are very, very limited. So globally, hydrates are found around these continental margins because of water depth and temperature. And the third requirement that we need is organic matter. A lot of organic matter so that methane actually is produced in the sediments. And that's why we find the distribution like it's shown on this map. And then, of course, we also have in permafrost regions like here in the in Tibet, or also in the Arctic, we also find hydrates because it's a lot colder than the usual temperatures in the marine environment. But the major part of hydrates occur along the continental margins. And this has driven several countries. These are the six most intense countries that put a lot of money into hydrate research in the past few years. That's India, South Korea, China, Japan, Taiwan, and also the US. They all have hydrates in their economic zone. And at least a few of them, like Japan, Taiwan, South Korea, they are quite limited in the conventional oil and gas reservoirs. So they are interested in hydrates because that will provide them natural gas as an energy resource, and they don't have to import it anymore, or at least less. Something we're interested in Germany and also in the US, the US is looking into that, is how to produce the methane from gas hydrates, not just by reducing pressure or increasing temperature in the reservoir, but by combining it with CO2 storage. Because when you inject CO2 into methane hydrates, actually it's a spontaneous reaction to CO2 hydrate and methane gas is released. And this is because the CO2 hydrate is more stable than the methane hydrate, and that's shown in this graph here. So this is basically what we're interested in Germany, to develop kind of technology for that. We have a large-scale project in Germany which is called SUGAR, Submarine Gas Hydrate Reservoirs, and we're looking into areas of exploration, better exploration techniques for marine gas hydrates, and exploitation techniques like also drilling and numerical modeling. And we're also looking into the transport aspect, because generally transporting methane, even also from small gas reservoirs, could be economical if the transport is not done with liquid nitrogen tankers, but in form of gas hydrates, actually. And this is funded in Germany by two ministries of economy and technology, and of research. And then another part we're interested in our institute at IFM GeoMar is the direct or marine options for storing CO2. So we have in Europe these depleted, worldwide, these depleted oil and gas reservoirs and deep saline aquifers, and that is already done on land, but also offshore, for example, off Norway by Statoil. And then there are options, of course, to go into continental slopes and store the CO2 directly as gas hydrate, so as a solid which is not cannot move, basically. And the more safe option, or the safest one, theoretically at least, would be to inject liquid CO2 into the deep sea. We're talking about 3,000 meter water depth, where the liquid CO2 actually becomes denser than seawater, so there is no buoyancy anymore. In all these scenarios, if CO2 is more supercritical or in gas phase, or even in liquid phase, it has buoyancy and wants to leak out. And for these reasons, to look at the impacts of leakage, potential leakage in the marine environment from CO2 storage side, we're also studying natural analogs. This is an example from the Okinawa Trough, where we have a hydrothermal vent that actually emits a lot of CO2. So you can see these small bubbles here coming out. And here we are already deep enough for hydrate formation, so that this leakage at the contact with the seawater from the rock actually freezes the CO2 as CO2 hydrate. This is natural CO2 hydrate. And we have applied on the EU level for a large project, EGU2, that is hopefully going to be funded soon. Then the third aspect that I want to introduce briefly, which is also a major part in our session on Friday, is the potential climate disaster due to melting methane hydrates in the Arctic. So the oceans are warming, we know that. In the past years, it has risen about 0.2 degrees centigrade, but in some areas, like near Spitsbergen, locally, actually the rise of temperature is around something like 2 to 3 degrees centigrade of this current. So that's actually an area where 2 years ago, and we had a talk about that last year here on the EGU, active melting of methane hydrates was found. And that basically looks like this. So if we warm the ocean and the bottom waters, then this is the original stability depth where hydrates form. So they form below, and only gas is only emitted above that stability zone. So if we warm the ocean, this actually means that the new stability, that we need higher pressures, larger water depths to keep hydrates stable, and the hydrates that are not stable anymore, they will start to dissociate and release also methane gas. So, which means that when we're warming the ocean bottom waters, we're shifting basically the stability boundary to a larger water depth in the end. And this is something that has been observed in the Arctic, and the Arctic has large amounts or large areas of continental shelves, so shallow water depths where the hydrates are stable because of below 0 degrees centigrade, and also a lot of methane is trapped below the permafrost ice. So we have hydrates and we have ice there basically, and methane is trapped below the ice as well. That's most likely also the larger danger than the hydrates itself. And these are melting and released into the ocean, and potentially also quite large fraction of that into the atmosphere. And with this, we move to the terrestrial environment now, and Helge will continue with that.
Okay, we already heard a little sketch out about terrestrial systems and that these are now becoming more and more important in terms of the global methane cycle. And here we see a few pictures again from the Arctic terrestrial environment that is somewhere in Siberia that you can look up, for instance, in Google Maps. And what we see here is a satellite picture. Here we have an aerial photograph taken from a plane. And we see now that large parts of these regions are covered by wetlands and lakes. And wetlands and lakes is more or less the same, except that a wetland would be a very, very shallow lake. And what colleagues from the US found out is that huge amounts of methane are released from these lakes, and that is, for instance, very obvious if you look in wintertime. Then these methane bubbles are frozen in the ice, and you can even drill these bubbles and ignite them. So apparently there's quite a lot of methane. And although our global budget estimates are, let's say, not really accurate, we know now that wetlands here in blue and together with lakes build the largest compartment of the natural methane emissions to the atmosphere. So this is all the natural methane, excluding all the anthropogenic sources. So apparently these are very important compartments. But unfortunately we don't know a lot about what is going on there with respect to the methane cycle. So I want to give you now a very brief sketch of a wetland or a lake. So what we have is we have a water column, there might be oxygen in it. Some of the lakes and also wetlands have an anoxic part, but that doesn't really matter. We have primary production in the euphotic zone, so here are algae produced. These may die off and then are sedimented to the lake or to the wetland floor. And then some microbes degrade this organic matter and methane is produced, which is then released into the water column. And we know that a lot of methane is consumed together with oxygen, but we now also have some indications that some of that methane is consumed under anoxic conditions. So that means that no oxygen is involved. So, as I said, the known pathway of methane oxidation in freshwater environments is the aerobic oxidation of methane. So we have methane and oxygen producing CO2. We also know that methane might be oxidized anaerobically, like we find that in marine environments together with sulfate, but this is most likely not playing a major part in freshwater systems because we have very little sulfate present there. And then some colleagues found very recently novel modes of anaerobic methane oxidation where methane is consumed together with nitrite or with oxidized metal species. But this was only done in laboratories, so we don't exactly know how important these are in the environment. But to give you a real-world example, this is from a South Alpine lake in Switzerland, very deep water column. And what we can see here is that oxygen is consumed in about 120 meters water depth, and that we have here in black we have methane consumption, and we see that exactly here where the oxygen is consumed we have a relatively high proportion of methane that's being consumed. But if we go deeper down into the lake, so some 50 meters beneath the oxycline, we find a second maximum of methane consumption, and that might be possibly related to the nitrate or the oxidized metal species. Of course, not all the methane that we have in these freshwater system is consumed, but some is then also going into the atmosphere. And then another very important part are plants, like for instance peat mosses, because here we have at the root systems we have some microbes that are sitting there and they are also consuming methane. So that's also a so far unquantified compartment in this methane cycle. But on the other hand, to make the story a little bit more complicated, we also have vascular transport of methane. So the methane is being diffusing into the roots of these plants and then is being injected into the atmosphere as well. So in the end, we of course need to know how important these different processes are and how much is released into the atmosphere. So very important questions for future research is, of course, how much methane is produced, how much is consumed in the water column and also in the sediments, what are the key microbes that are associated to these different biogeochemical pathways. We have different tools now, genetic tools, lipid biomarker tools, stable isotope tools. We also need to know exactly what the role of plants and other bioturbating organisms are on methane emissions, what these key microbes are that are sitting together with the roots of the plants, how important these microbes are, and of course also what the source strength of these different wetlands and lakes are to the global methane budget. And we now have some different satellite techniques and atmospheric modeling techniques in order to find out about more. And we now come to a next terrestrial system, and that is in the deep subsurface, and Martin will talk about that.
Okay, so there have been in the last decades increasing evidence collected or presented about widespread occurrence of the formation or biogenic formation of methane in deep systems. Deep systems, in this case, I'm considering mainly oil and coal reservoirs. And why is this important for us? First of all, one reason is One reason is that, for example, methane emissions from coal mining activities contribute around 8% to global methane emissions. And with increasing coal mining activities, which have to be expected, especially in China or India, these emissions are likely to increase further. Another important aspect for us is that methane is a more climate-friendly fuel. So if compared to coal or oil, the burning of gas leads to much lower CO2 emissions than with the other fossil fuels. Another point is that the availability of common fossil fuels, oil and coal, is limited. And we see here the prediction of the oil production over the next 50 years. And depending on what kind of resources you introduce into your calculation, the peak of oil, that means the time point when the production of oil is lower than the actual demand of oil, is coming at around 2020 or maybe 2040, but still in the lifetime of many of us. So another fact is that generally 50 up to 70% of the oil at the moment remains unproducible in reservoirs, so it cannot be recovered. Also, the majority of oil that is left at the moment is heavy oil or unconventional oil, like oil sands or very deep reservoirs, which at the moment are very hard and, if at all, very expensive to recover for energy production. The same is basically due with coal, and a colleague once formed the term stranded energy assets for this kind of reserves we still have. And from this we deduce the need for the development of new production technologies. And since the majority of the oil or energy fossil fuel reservoirs are very limited in the local distribution, so mainly in Middle Asia, we also need a diversification of the energy supply to get more independence from these countries. And from this, for this, we suggest especially one process as a small contribution, and this is the microbial conversion of oil or coal to methane. We have seen a lot of science for microbial activity, for example, in oil reservoirs. So a lot of very big oil fields, some examples are listed here, are actually biodegraded by the activity of microorganisms. Also, we could show the activity or the conversion of oil into methane in the laboratory. So we see the formation of methane when we add oil as a substrate. If we don't have oil or if we inhibit microorganisms, we get no formation of methane. And looking at the oil, we can see that different fractions of the oil are preferably degraded, like the alkanes, and are disappearing in the time course of these experiments. So also the composition of the oil is getting changed. We made similar observations in coal mines. Here are some pictures from abundant coal mines in Germany in the Ruhr Basin, where we had the possibility to enter the closed mines and took samples from there, coal samples, mine timber samples. And again, we could see these methane-producing organisms sitting around coal particles. We could isolate the organisms, identify them, and so on. So our idea, or what we are working on at the moment, is really to find ways to stimulate or also if needed to inhibit microorganisms degrading hydrocarbons, oil, coal or black shales into finally methane or carbon dioxide, and then use this methane for energy production. And this is just a very simple scheme. So with the production equipment still in place, we could introduce nutrients into oil or coal reservoirs, and later on, using the same equipment, recover the methane produced from the oil and the coal and use it on site or wherever for energy production. So to conclude this, we have seen, or we can see that the microbial conversion of oil to methane is a natural process and widespread. So we have many degraded oil and coal reservoirs. We could show in the laboratory that it is possible to stimulate methane and coal conversion to methane. So we have an idea how to do this in the field. The stimulation of this process in the field has the potential to recover a significant proportion of these stranded energy assets. So to further explorate the so far not recoverable oil or coal reserves. And also the methane-fired power stations have a much lower CO2 emission than coal or oil-fired power stations, so they are more environmentally friendly than the other types. And what I've not mentioned today, but which will also be a topic of the session on Friday, is that other sources of unconventional methane gas are more coming into focus of the oil or gas industry, especially shale gas, but also tight gas or aquifer gas, which are more new targets for exploration activities, also in Germany or in Europe. And that's it. I can have to conclude now with just the hints on our sessions, and yeah, slightly more time.
All right, thank you all of you for your interesting presentations. We now reached the question and answering section, so if there are any questions for the scientists involved, please go ahead.
I'm Stefano Tanzani from Nature Publishing Group. I have a question about the use of methane in methanogenic deposits for fuel. Some of these environments that you guys described are relatively extreme. I mean, you're talking about continental shelves that are 400 to 4,000 meters. That seems already rather difficult in the sense that we're seeing offshore oil developments like the one that caused the oil spill in Louisiana, which was about 1,200 meters deep. And so, I mean, what's the status of the technology? How ready is it to get there, I would say? And what are the possible side effects that an extraction of these kinds of deposits can cause?
Regarding the limits of this technique, I mean, the only real limit at the moment for microbial life is the temperature. So reservoirs or zones which are hotter than 120 degrees are not suitable for this kind of techniques. And side effects of this application would be that the oil composition changes. So the oil is losing quality. It gets heavier because the lighter fractions are removed by the microorganisms. But we suggested as methods for reservoirs which cannot be produced anyway at the moment, or which have been produced to the farthest extent and cannot be produced anymore. So in this way, it would not be a loss of oil, considered this way. Other side effects at the moment, I don't know really what to expect. And we are currently moving from small-scale lab experiment to sort of intermediate-size experiments with larger soil columns and to constrain the budgets and so on. Yeah.
But I think you were referring to mining gas hydrates on the continental slope, right?
Yeah.
I mean, of course, there are quite a few.
I mean, in the Arctic, we have caprock, real caprock. The ice is doing that job for us. So there, conventional gas and oil techniques can be used and applied, and that's going to start this next year in the US and also in northern Canada. We had these exploration wells. The US is also going to do that in some next close future and near future in the Gulf of Mexico, which is then in a marine environment. Japan is thinking about doing that in the Nankai margin, but for something like slope stabilities, even how to actually secure the wells, this technology needs to be developed. So that's not readily available.
The most, let's say, significant risk is a leakage, because to get the system completely closed is nearly impossible, excuse me, on this stage of development, and it's leakage of both. So if you want to take methane out, for instance, gas hydrates reservoirs, methane can have very good possibility to leak in the water column, vice versa with the CO2, which with the CO2, that's another problem with the sequestration thing, is let's say, almost ideal geological structures, which as I know, currently existed only 2 stable over years in the world. It's one is Satoil project in North Sea, and another it's Dutch project, which is I think they're injecting since 1987 or so. It's not far from Amsterdam, North Sea. The rest is all very questionable. So.
All right. Are there no more questions? Then this will conclude the press conference. Thank you all for your time and thank you all for your time and attention. Oh, you have one more question.
You guys have talked about natural sources of methane, and of course, I mean that brings the question: what's the balance between natural sources and anthropogenic sources? Meaning human emissions and meaning animal emissions. Animals are farmed, obviously, for
very
various
easy
sources.
answered.
Yeah. What's sort of the ratio between the two?
It's more or less 1/3 natural emissions and 2/3 anthropogenic induced emissions, including mining activities and oil drilling activities. So cattle farming of ruminants, so basically cows, is almost on the same order as the entire emissions from wetlands. But as I tried to point out, the source strengths of these different environments are not really clear at the moment. So we know, for instance, from that very recent publication which found heavy gas seeps along the East Siberian margin, that at that point of time, when they measured that and when they did their interpolations, that it seems that the amount of methane that's coming out there is almost as high as the total emissions to the atmosphere, which of course cannot be true, because you would see that in stable isotope records. So either we have a very big bug in our estimations of source strength, or that is just an episodic event which we just overlooked, which is rather unlikely.
But they're all very episodic, because within this experiment that was on Monday, so Natalia Shakhova, she did a presentation within her session, and she said that on this spot, so they had a few hot spots, and it was within one cruise actually. So they went, they measured water column, which was extremely oversaturated with the methane, and then next day they came and there was nothing. So it's all episodically. And then a day later they came again and they met the same oversaturation of water column with the methane. So they just put a sonar, special sonar on the seafloor in a hot spot, and they, for not very long time, but just then the sonar actually fixed the pulses of methane outcome. But this is another question which pointing back towards sources and sinks, or sources of methane, that it can seep everywhere. Triggering mechanism is not known, and that's also in Arctic become to be quite hot, let's say, is because nobody really looked at it years ago. And actually the interest went back to the methane global budget only when we started to trace that suddenly, nobody knows why, after 1999, so methane started to, after 2007, methane started to rise, and 1999 till 2007 it was stable. So it stopped, and that was also an answering question. So
a big problem that we have right now is that all these global estimates are, let's say, back of the envelope calculations. Mm-hmm. And that some of these assumptions are rather rough, and while you're using these assumptions and you're doing calculations and modeling with this, you have, let's say, an exponential mistake that is going through all your calculations. And like, I mean, probably someone looked on the amount of methane that's been released from cows, and then just made a very rough assumption on how many cows there are on the earth, and that's probably already a very good assumption. But if you have a pond that you, let's say, go out here to in Vienna and you look for a pond that's emitting methane, that's not the same type of structure that you find in Siberia or that you find in the Alps. So we really need very good, well-constrained, let's say, regional studies, and we have to be careful to extrapolate that on a global scale.
Globalization in this peculiar case doesn't really no.
It's, let's say, difficult. And
yeah.
Okay then. If there are no more questions, just one more question. We've got time for one more question.
Given the greenhouse gas potential of methane, there were two talks that hint at the way to use methane as an energy source from hydrates or from this the bacteria you talked about. Are you confident that you will be able to control these techniques enough that you don't have a catastrophe with enhanced greenhouse gas emissions? And if so, when will that be?
Yeah, the when will that be question for hydrates is probably a bit more difficult to answer. I mean, the most driving force for that is where is enough out there that actually investing large scale is actually worthwhile doing it. So in the permafrost regions, I think that will happen, and there we have natural cap rock, so they can actually apply the standard oil and gas techniques. In the marine environment, it's a different story. We don't really have, in most occasions, a real hard cap rock on that. It's soft, more or less soft sediment, but it's muddy sediment. So, and the difference to gas reservoirs, the conventional gas reservoirs, is they are not under pressure. So if we dissociate, we need to work at low additional pressure to the one in the environment, and that's the thing we have to learn how to control that and work properly on that. But that is probably doable in something like 10 to 15 years. But you can always have failures like we've seen now in the Gulf of Mexico with that platform, which arise by a succession of human errors. So and you will never really be able to completely exclude that. That's not possible. But there are ideas how to approach these problems that we have in the marine environment with exploiting gas hydrates, but that will take a few more years.
May I comment a bit more in terms of melting of permafrosts and formation of these lakes, which are called thermokarst lakes? Actually, what Geosciences says that permafrost has its effect of self-preservation. So it melts till this certain, but it's, let's say, that a lot of Geoscientists, they are a bit skeptical about this big boom melting theory. It happens, but it will not happen that permafrost is disappearing completely. So the self-preservation is based on that the upper part of the permafrost is melts, and then it makes a kind of like a water pillow or cap, and then this water protects the rest of the permafrost from the melting. So in fact, of course, during the initial melting, you have these cracks and the pathways, which, because permafrost is also like acting as a cap rock, so some gas escapes, or it's induced the rise of temperature, so it's induced microbial production, but it will take a while in scale, not of life, even of people life, so it will take much more year if you're afraid that it will go completely melted. So.
And maybe to the in situ conversion of oil and coal via microorganisms to methane. I mean, these coal and oil reservoirs, they are normally closed geological systems, so otherwise they would not be present at the moment.
Yeah.
And for this, we would need no new development of technologies. So all the common gas or oil production equipment in place is well established. So there would be no need to investigate or develop new technologies for this.
Okay, then we've now reached the end of this press conference. Well, thank you for your time and attention.
Thanks. Thank you for coming.